Hi, I'm Courtney Reed, and I'm happy to welcome you to a discussion of our paper, Surface Electromyography for Direct Vocal Control, with my co-author Andrew McPherson. I'm a PhD student at Queen Mary University of London, and I'm especially happy to be here virtually, as this is my first NIME conference ever. Our paper discusses the application of surface electromyography for direct interfacing with the muscular vocal mechanism, and verifies this as a way of detecting vocalized and imagined singing. This presentation will begin by defining direct and indirect control, look at current work in vocal interfaces. Then we'll introduce a way to address the current design gap in voice controllers with electromyography. It is important that we first set a solid definition for both direct and indirect control in DMIs. We can start back at the general definition for direct manipulation and control within HCI. Direct manipulations are those which are easy to see, rapid, and use mappings of user input to computer output which mimic interaction away from a digital context. The electronic violin here relies on audio amplitude to control filter parameters in this duet with the radio baton. Compare this with the McPherson K-bow, which generates MIDI data based on bow position, acceleration, and grip sensing. The Matthews violin is an example of indirect control. Its audio-driven signal analysis relies on translation of the amplitude to control filtering. The user input must be analyzed and parametrized, and the role of feature extraction is critical. In the case of the K-bow, we see direct control aspects. There is no parameterization in the use of these sensor measurements, and input from the user's performance gestures are mapped to corresponding controls. Our key distinction, therefore, between the two types of control is then this idea of translating user input. We thus define indirect control as being those cases where user input is analyzed and features are extracted. The mapping may not occur in the same direction, and the user must therefore learn an abstract mapping for control. And direct control we would define in places where user input streams directly influence a related parameter, and the mapping moves in the same direction as the input. These methods of control can of course be combined, and most DMIs rely to some degree on both of them. The Subvocalisation, as an augmented violin, utilizes bow direction detection with electrodynamic pickups on the bridge, pitch tracking via finger placement on the fingerboard, and also on parameters extracted from the audio signal. Direct control offers many advantages when incorporated into design. Not all interactions, in the case of ancillary gestures, will produce sound, so not every action can be analyzed or used by audio feature extraction alone. Audio analysis can introduce latency, and the idea of audio-based synthesis implies that there is an organic signal which needs to be competed with. Having mentioned all of this, I want to again reiterate that we should not define indirect control as being audio-based, but as being feature extraction-driven. Vocal interfaces generally fit into two categories. The first being synthesis interfaces, which use characteristics of the vocal signal as a controller, and the second being interfaces which are seemingly non-vocal, being used to generate synthesis of the voice. The first group of voices as controller would include vocoders and talkboxes, and some familiar NIMEs such as the mouthicizer, which uses facial and mouth tracking to control multitudes of synthesis parameters. Other digital tools would include plugins like the Vox by Waves, or tools like Imitone, the vocal equivalent of the MIDI guitar. The second category of voice controllers are interfaces for controlling vocal synthesis models, which rely on other methods of control, mostly using the hands or manual selection of formants. Another great example is vokinesis, where this type of control has been turned into a performance art in its own right. With the roof right over our heads, we'll share. Somewhere in between these groups of instruments we see a clear gap. Control of synthesis using direct vocal control. And there's a reason for this. We don't normally examine direct qualities of the voice when we think about singing. It's difficult to see what's actually happening when someone sings. When we do look at voice physiology, most analyses are done with medical equipment, such as ultrasound machines and invasive intubation procedures to look at the vocal folds. Not something you necessarily want to be doing during a live performance, although I'd be happy to volunteer my own voice if someone wants to organize this. For these reasons, we propose using surface electromyography as the basis for interfacing with vocal musculature and for direct vocal control. With EMG, we observe the electrical activation of the muscles. In surface electromyography, this can be done with electrodes placed on the skin, making this relatively non-invasive. We've seen EMG in action in the study of performance gesture and control, as well as in composition. We are able to use EMG for gestural-based mappings, and in performance, users of EMG devices are able to quickly learn how to adapt their movements for well-defined control. EMG is also relevant in voice research, as it has been shown to be able to detect subvocalization. Activation in the brain when imagining an action is similar to when actually executing the action. Therefore, we see activities in muscles during mental exercises and rehearsal of an action. This is what we call subvocalization when we're talking about imagining speech or singing. In the case of the voice, this activity can be observed with EMG, and use of this method for interfacing with the body can provide insights into mental rehearsal technique and anticipatory action. In our paper, we show EMG taken off the omohyoid, one of the lower neck muscles. The omohyoid is part of a group of muscles which lowers the larynx and is active as singing moves into the lower registers of someone's voice. These plots demonstrate an exercise where I sang some descending pitches at the bottom of my range. The left plot is voltage taken from singing these long tones. We can see the activation of the muscle as the larynx lowers when I breathe, the onset of the note as my larynx moves into position to sing each tone, and the relaxation in the muscle when I stop. In the final note, I did not breathe before singing, and so we also see no indication of breath in the voltage. In the rightmost plot, we have the voltage from the same exercised but imagined and not sung aloud. We can see the same vocal activity in 3 notes here. Although this lies within a smaller voltage range, the occurrence of these 3 notes during subvocalization are still present in the EMG signal. If we don't want to focus on pitch, EMG can also be used. The suprahyoid region under the jaw, where the base of the tongue lies, is responsible for articulatory functions needed for text. As well, deep breathing and singing and expansion of the resonant space in the mouth is done by dropping the tongue, as you would during a yawn. We can see this function while singing articulated staccato notes. Ah, 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 ah. 2 easy things to spot in all of the suprahyoid activity I'll show you are the movement of the tongue to widen the throat during deep breathing, and the resetting of the tongue position at the beginning of vocalization. Then, here, with each note, we see the tongue moves to support the light glottal stop needed for the staccato, and the movement to the next note in the sequence. The starting note does not appear to impact this execution much, as we see the activations for each iteration lie in the same voltage range. In this case, the suprahyoid is acting as an articulator to achieve a staccato. Even if I force myself to sing very low in my range, this set of muscles retains their articulatory function. In the second example, I sing a pattern of alternating consonants, ta-ka, ta-ka, ta. Ta-ka, 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 ta. Again, we can see the same movement with the breath on the positioning for vocalization. Each note here involves a consonant attack, and then the sustained pitch. Between each note, the tongue must move from a front of mouth t to a back of mouth k. We see this movement in our EMG signal. And, if I imagine doing this, the breath is still present, and we see some small activations where the consonants would lie when I subvocalize. Ta-ka, 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 ta. Ah, 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 ah. We can see patterns of exercises in the case of this descending scale vocalise, and also that this pattern remains visible in subvocalization if I imagine singing a couple of these. We see that we are able to observe small signals during singing exercises, as well as during subvocalization. Through EMG, we hope to begin bridging the direct control gap when it comes to voice controllers and instruments, and hopefully bring visibility to the vocal mechanism in a new way, which can potentially be used in both creative and educational contexts. I look forward to presenting to you in NIMEs to come on the progress of this work in identifying more vocal mechanics and in applications of EMG in singing. My PhD focuses on acquisition and application of mental imagery in vocalists, and so I hope to especially share some imagined singing and subvocal activity in the near future. The circuit we are using is continually changing as we learn more about what is possible with EMG in this context, and I'd be happy to share this ongoing progress with anyone interested. There are potential applications in a number of fields using the current system, including study of performance gesture, rehearsal and practice techniques, linking biomechanics to voice pedagogy, and for sure some creative performance and instruments which blend these 2 types of control, in both voice performance and other musical practices. Thank you for tuning into this presentation. I look forward to hearing your thoughts and feedback on this research, and please do feel free to ask any questions or contact me about EMG and voice-related work. Thanks again.